Having seen epsilon as a general property of a material, we see a special material called as free space or vacuum. Free space or vacuum, or the air around us. Yeah, the air around us. That has a special permittivity symbol called as epsilon zero. The zero refers to free space. Free space or air, the air around us. And that value is 8.854 into 10 per minus 12 farad per meter. But how about if it's not air? For example, wood. You know that wood is not a conductor, electrical conductor, so it's a dielectric. Or how about for plastic? Or how about a printed circuit board? So those can have an epsilon which is typically greater than your epsilon zero, that of air. So what you do then is you divide that epsilon by epsilon zero. You reference that to that of air. You reference that to that of air, and you define that to be the relative. You call that the relative permittivity or dielectric constant. Both are the same, relative permittivity or dielectric constant of a material medium. And since it's the ratio of the permittivity of the medium, which is farad per meter, and the permittivity of free space, which is also farad per meter, they cancel each other, and this guy becomes dimensionless because it's a relative term. So, for example, there are materials called as Teflon used in coaxial cable that carry RF energy. Those have an epsilon R of, let's say, 2.2. The material is called Teflon. You might have heard FR4 PCB, printed circuit board. Yeah, that FR4 will have a dielectric constant of, let's say, 4.4 or 4.5. So different materials have different dielectric constants. And what happens if you're not looking at free space but electric field in that material? If you were to find the electric field in that material, remember we used to have 1 over 4 pi epsilon naught. This epsilon naught is no more epsilon naught. It has to be epsilon because that is the material. If I have a certain material of certain a volume with epsilon equal to epsilon or epsilon naught, then the electric field due to this Q charge inside the material is going to be 1 over 4 pi epsilon Q over R square, proportional to 1 over R square in the R hat direction. Now that you see, every time I define this electric field, I have this material property here. Q is the source of the electric field. This is the distance, 1 over R square distance. But it is not only that, it's also proportional on the dielectric constant of the material. So this electric field is, you can't generalize it just purely based on a charge and its location, because it additionally depends on the permittivity of the material. Instead, if I were to define a new parameter D called as the electric flux density, if you define electric flux density as simple as epsilon times E, then this D becomes independent of permittivity. It is purely because of a charge and its location. It's purely because of a charge and its location. The permittivity is absorbed. What do we mean by that? So you know that E is 1 over 4 pi epsilon naught, 1 over R square in the R hat direction, Q over R square, epsilon naught, epsilon R. So if I were to multiply this and bring it over here, my epsilon naught, epsilon R E is nothing but 1 over 4 pi Q over R square in the R hat direction. And this is what I'm going to define as D. So it's only dependent on charge and its location. So electric flux has that advantage. So that's why people define either the electric field or the electric flux. So whatever that you did for the electric field, for point charges, or for line charges, for surface charges, for volume charges, is all the same. It is just that never in the right-hand side, you will see the epsilon naught or epsilon R, epsilon naught. You will not see them because that is getting absorbed in this guy. What you define here is epsilon E. So again, for a line, it's for a line charge rho L. This is this. For a surface charge, this is rho S. For a volume charge, it's going to be rho V.